Alright, this is paper 1, part 3, the hardest part, and also the introduction to the concept of section B of an exam paper. So you'll have noticed that section A contains very short questions with not very many marks in them, and the questions, they tend to stay within a single topic, or maybe two. That all changes now, because when we move to section B, there are some things that make that part much harder. First of all, the questions are super long. They go on forever and ever. So this one is a 15-mark question. That's more than double of most of the section A ones. And also they skip around topics in a way that you cannot possibly predict. So please don't try, because you'll just get super confused when something very unexpected happens. Just take each step one at a time and see what it is they're asking and just focus on doing that. That's the main good advice for handling these section B questions. And second, try not to fall asleep midway, because that's also very likely to happen. Another thing you have to notice is that it says on top of the question to not write on these pages, and that's actually very serious, because I've heard rumors that sometimes the people who correct your exam questions, they get a digital scan of your answers, and they have all sorts of computer programs that automatically extract your answers from the answer booklets and from the exam papers and sort them in a way that the examiner only gets to see answers for one question at a time. Sorry, I have to attend my dog. So that means that whatever you write on this page, nobody's ever going to see that, most likely. It also means that when you write your answers in the answer booklet, it's extremely important that these little boxes that you have, you fill out these boxes with the question number for the question that you're answering. And again, please think that this is because there might be some machine sorting your answers. And machines, as you all know, are pretty stupid. So they just do exactly what they're instructed for, and they cannot ever engage in thinking what you probably wanted to have written and what your answers might be for. So handle it like that. Anyway, let's dive into the first one of the two section B questions, number 8. So I'm trying to write over here as if it were my formula booklet, and I'm sorry I couldn't get a proper formula booklet, so the boxes in the left side, they look something like this. And when we start working on this, you're going to write with your neatest handwriting that this is your answer to question 8. Question 8 gives us two functions, f and g, defined by some logarithm business. And in g, there is this constant d that we don't know what it is, except that it's a positive real number. Then question A says, state the equation of the vertical asymptote to the graph of the g function. So you write something like question A, and when it's a state, you don't really have to argue or write any reasoning. It's also only a 1-mark question. You just have to write the right answer. So the function g, this is paper 1, so you can't grab your calculator and draw the graph, but it's a logarithm minus something that is just a constant. So the graph of this function is just a logarithm graph that has been scaled by a factor 2 and then moved downwards with whatever ln of 2 times d is. And we get a little bit of hint for our thinking when it says that d is a positive real number, because that makes us remember that the logarithm is only defined to positive numbers. You can't take a logarithm to 0 or something negative. And if we remember what the graph of the natural logarithm looks like, then we know that it has a vertical asymptote that is the y-axis. And that's what we have to realize, that even though we scale vertically and move the graph vertically, then that doesn't really change where the vertical asymptote is. So the answer to this question is that the y-axis is the vertical asymptote to the graph. And the equation for the y-axis looks like this. So that's the answer to A. Notice that you have to give an equation when they ask for an equation. So if you just write 0, that's not good enough. Anyway, the graphs of f and g, they intersect at 2 distinct points. And then for question B, part 1, they say we have to show that the points of intersection at those points, then this equation is fulfilled. So points of intersection, they happen in x coordinates where the two functions make the same function value. So we are going to set up the equation that we use to find x coordinates for points of intersection, just saying that we want f of x to be equal to g of x. And putting in f of x, then it says ln of 2x minus 9 equals 2 times ln of x minus ln of 2d. And that's a lot of logarithms. But if we recall rules for logarithms, then we might remember, so the left-hand side, we can't really do much about it yet. But the right-hand side is a difference between, well, first of all, we have 2 times a logarithm. That multiplication by 2, we can actually move it into the logarithm as a power tool. That's using the rule. It's kind of backwards to the way we normally use it, or most commonly, but it can be used in both directions. So this is ln of x squared. When we subtract another logarithm, we can actually turn that into one single logarithm where we divide the two things. So again, we're using it kind of the opposite direction that we normally do, but this is the same as the logarithm of x squared divided by 2d. And that's nice because now we have two logarithms that are equal to each other, and that only happens when the interior thing in the logarithm are the same. So the equation is the same as saying that 2x minus 9 is equal to x squared over 2d. And then we can multiply with 2d on both sides, and we can put everything on the right-hand side. So we get 0 equals x squared, then minus 2d times 2x, that's 4dx, and then minus 9 becomes plus 9 over here, plus 9 times 2d, that's plus 18 times d. And that's exactly the equation they wanted us to find. So that's for by. So part 2 says, hence show that 2d squared minus 4d is larger than 0, is bigger than 0. And for that, we kind of need to go back and realize that we are being told that the graphs are intersecting at 2 distinct points. That means that the equation we have right here, this equation, must have 2 solutions for x. And then we think, well, it's a quadratic equation. Notice how quadratic equations just keep coming back. It's a quadratic equation, and that has 2 solutions when the discriminant is positive. So what we want to say is that the discriminant of this equation must be positive, and the discriminant, that is the coefficient to x, that's minus 4d squared minus 4 times the coefficient of x squared times the constant coefficient, 18d, must be positive. And then we can kind of see that this starts looking a whole lot like the equation they have. We get 16d squared, and then minus 4 times 18, that is 72, times d is larger than 0. And then we just divide by 8 on both sides. So here we get 2d squared. and 72 divided by 8, that happens to be 9d, is larger than 0. And since 8 is positive, we can actually divide by 8 on both sides of an inequality and keep the inequality the same. And that is what we had to show. So for B3, we have to find the range of positive values of D. And that is really just saying now we have to find the values of D where this is fulfilled. And that means we have to solve an inequality where the left-hand side, that's actually another quadratic expression. So in this case, we could kind of think that D is the variable here. We could imagine that it's an x, and it says 2x squared minus 9x has to be positive. And then we could visualize what the graph of this function looks like. It's a parabola, it's concave up because we have a positive coefficient to d squared. So if we find the places where we have the expression equal to 0, then we could kind of make a little drawing. Then, if the parabola looks something like this, if we find the two places where the expression is equal to 0, then we know that the solution to the inequality, they are the numbers of d that are on the right side of this one and on the left side of this one. That's the thinking we do. So we actually solve 2d squared minus 9d equal to 0. And one solution is that d is just 0. That's what I also put into the drawing over here. And the other one is that 2d is equal to 9. That is that d is 9 over 2. And now we have the solutions to the equality, and then the solutions to the inequality is that d must be either smaller than 0 or d must be bigger than 9 over 2. And the question keeps going, because now in the following diagram we have parts of the graphs, and we can see how this vertical asymptote to the graph of G is the y-axis, as we said in question 1, so that's a nice confirmation. And we're being told that the intersection points, they are P and Q, where P is the smaller one. And then we have to consider the case where D is equal to 5. So now D is 5. That's just such a random thing that you cannot possibly predict that they are going to suddenly tell you that. But they do. So now D is 5, and we have to find the value of Q minus P. And express the answer in a certain form. So D is equal to 5. Let's roll up. I have a bit more space here on my answer booklet page. You would probably have to go to a new page, and then it's very important that if you do, then you fill in the box with the same question. I have the luxury of doing this. For C, when D is 5, then the equation that we are solving actually becomes very concrete. To find the values of x, we solve x squared minus 4 times t times d, that's 20x, plus 18 times d, so 18 times 5, that's 90, equals 0. That's how to find the x coordinates. So in fact, when we solve this quadratic equation, then the solutions we get, they are actually the values of P and Q. So we just fire up whatever we do. I like to do, especially when this guy is an even integer, finishing the square, so x minus 10 squared, and then we subtract 10 squared, that's minus 100, plus 90 is 0. So putting that on the other side, we get that x minus 10 is equal to plus or minus the square root of 10. So x is either 10 minus the square root of 10, or x is equal to 10 plus the square root of 10. And that's the value of P and Q. So since this is the larger one, it must be q. So if we calculate q minus p, that's what they ask for, then we do 10 plus the square root of 10, and we subtract 10 minus the square root of 10. Notice that how important the brackets are. So when 10 and 10 subtract, they disappear, and we just get 10 plus square root of 10 plus the square root of 10. That's 2 times the square root of 10. And that's actually on the form they wanted, which is an integer, positive integer, times the square root of another positive integer. So that's the answer for part C. Question 9 is no doubt the hardest question in this set, and I don't think any of you managed to get all the way through that question. It's fully understandable, but I would like you to not find me unreasonable for putting it in the test, because it actually involves nothing that you haven't learned, and you should know that this is the difficulty that the hard questions on the exam go to. So this is actually more or less, I changed a few details here and there, but it is a question that was on an exam a couple of years ago, and you can kind of feel bad for the poor students who had to sit and work all this. But let's try and dive into it. So we take a little box and we say bravely that now we're answering question 9. First, it says find the binomial expansion of this stuff. So that should be kind of cosine of theta plus I times sine of theta, all of it to the power of 5. It should be more or less automatic because we have two terms in the bracket, only we could get confused because one of them is imaginary, but the binomial formula works equally well with imaginary numbers. So hitting this with the binomial expansion formula actually is completely straightforward. You should be careful not to try and be too smart here, because I see many people going wrong places, first by thinking we have this de Moivre theorem that says that this is actually cis of theta. So when we raise that to the 5, we are just going to multiply theta by 5. But that's what question B is about. So you're starting to do things that is not what they ask for right now. And I also see people who think it would be so much nicer to put this on polar form. That's more or less the same as the Moivre's theorem. But again, you're not doing what they ask for. We have a binomial with two terms, and it's raised to the power 5. So they want us to do an expansion. So you should really just say, well, the binomial formula says we can call it k now, from 0 to 5, and then 5 choose k, the binomial coefficient, times cosine of theta, let's say to the power k, and then times I sine of theta, that's the other term, to the power 5 minus k. That is the business we have to go through, and this becomes long, because now we want to write up, they say we have to give the answer in the form a plus b times I, where a and b, they are expressed in terms of sine of theta and cosine of theta. So to do that, we actually need to write up all the terms. So the k0 term, that's 5 choose 0, is just 1, and then we get cosine of theta, actually to the 0th power. So the first term I get will be I sine of theta to the power 5. Then comes 5 choose 1 times cosine of theta to the power 1 times I sine of theta to the 4. Then we get 5 choose 2 cosine theta squared plus I sine of theta cubed, and it just keeps going. 5 choose 3 cosine theta cubed I sine of theta to the power 4. 5 choose 4 times cosine. I just made a mistake, didn't I? I made the power up here. This power should go down each time, so now it's to the power 2. Then we get cosine of theta to the 4, and I sine of theta to the power 1, and finally the last one is 5 choose 5 cosine theta to the power 5. That is the whole thing, and we need to calculate this. So let's try and do everything at once. So we need the values of the binomial coefficients, and you should probably get to a point where you could just calculate all of them in your head. But I've seen a few people doing this, and you'll see me, like for the first and last time, when it is 5 choose things, it actually makes a little bit of sense to do this stupid triangle. That 4, 6, 4, 1, and then the essential one, 1, 5, 10, 10, 5, 1. These are your binomial coefficients. Thank you, Pascal. That should be filled in here. Then the powers, let's already realize that we want to divide the real parts and the imaginary parts separate. The powers, when we have an even power of I, so that's I squared and I to the 4, that is going to be either plus or minus 1. So this term is going to make a real number because we get I to the power 4, that is just 1. This term is going to make a real number but with a negative sign because I squared becomes minus 1. And then this guy. These are the real part, and if we try and write those up, then the real part becomes 1 times cosine to the... Let's do this one first. We get cosine of theta to the 5. That's from this guy. Then we get, here we have I squared. That makes a minus. Then we get minus 5 choose 3. That's a 10 times cosine of theta cubed times I squared is the minus. So sine of theta squared, and finally this guy up here is plus 5, that's the binomial coefficient, cosine of theta times I to the 4 is just 1, and then we have sine of theta to the 4. And it could just fit there. That's the real part, plus, let's move our I outside a bracket, and say the imaginary part comes from here. I to the 5 is equal to I, because I to the 4 is 1, and then we have one more factor I. So this guy becomes sine of theta to the 5. The next imaginary part is from this term, where we have I to the 3, that is going to make minus I. If we have I outside the bracket, then we just have a minus left. Then 5 choose 2 is 5 times cosine of theta squared sine of theta cubed. And finally 5 choose 2 is a 10. So let's regret that and say 10 of those, and the last term that makes an imaginary part is right here. It's just this guy with the I outside a bracket. 5 choose 4, that's a plus 5 cosine of theta to the 4 times sine of theta. And that's really it. The real part is this stuff, and the imaginary part is this stuff. Then for question B, it says, by using de Moivre's theorem and your answer to part A, show that sine of 5 theta is equal to this stuff. And that contains, there's a reason this is a 6-mark question, because first you think, well, I'm really good at de Moivre because I know that the stuff I just calculated, so cosine theta plus I times sine of theta, also known as cis of theta to the power 5, is actually just equal to cosine of 5 theta plus I times sine of 5 theta. So we know that the real part is just cosine of 5 theta and the imaginary part is just sine of 5 theta. So when we have the real part here and the imaginary part here, we know that sine of 5 theta must just be the stuff that is the imaginary part. So it's equal to sine of theta to the 5 minus 10 cosine theta squared sine of theta cubed plus 5 cosine of theta to the 4 times sine of theta. And then we think that's really it. We have found the value of sine of 5 theta. But it's not the expression they want. And we ask ourselves, what's the difference? Well, in their expression, there are only sines. And we have both sines and cosines. So there we need to think, how do we get the cosines to be sines? And the answer to that is, of course, that sine squared plus cosine squared equals 1. That means that the cosine squared is equal to 1 minus sine squared. And the cosine to the 4, that's cosine squared squared. So that is 1 minus sine squared of theta, all of it squared. So now it gets hairy. This is equal to, I'm going to need many lines. First we have sine of theta to the 5. That one is not so bad. Then we have minus 10 times 1 minus sine of theta squared times sine of theta cubed. And then we have plus 5 times 1 minus sine of theta squared, that was cosine to the 4, times sine of theta. And these, well, the first one is just directly expandable, so we get sine of theta to the 5, then we get minus 10 sine of theta cubed from multiplying this with minus 10 and the 1, then we get minus 10 times minus sine squared, that's plus 10 times sine of theta squared times sine of theta cubed, that's sine of theta to the 5. And the last one we get is plus 5 times, and this is really nasty. So the squaring here is actually 2 terms subtracted squared. So that bracket is 1 squared plus sine of theta squared, that is sine of theta to the 4, minus 2 times the double, so minus the double product, so minus 2 times this. That is 2 sine of theta squared, all of that times sine of theta. And we can kind of see that when this sine of theta goes into the bracket, we get a sine of theta times 5, we get a sine of theta to the 5 times 5, and we get minus sine of theta cubed times 2 times 5, that's 10. So we can... So the thing is, we have the answer, so getting the right answer doesn't give any points. So we should actually write up just one more where we collect the sine of theta to the 5, and this sine of theta to the 5, that's by now 11 sine of theta to the 5 minus 10 sine of theta cubed, and then say plus 5 sine of theta plus 5 sine of theta to the 5, and finally minus 10 times sine of theta cubed. And collecting these, we have 11 plus another 5, that is 16 sine of theta to the 5. Then you have minus 10 sine cubed and minus another 10 sine cubed, that's minus 20 sine of theta cubed, and then we have these plus 5 sine of theta. And I hope and pray that that is exactly the stuff they wanted. Now the question just keeps going and going. Now for CI, they say hence, so we probably have to use the fact that sine of 5 theta is equal to this long stuff we just got. But now we have to show that theta equals pi over 5 and 3 pi over 5. They are solutions to the following equation. And that equation is not quite the same. But we realize that this equation that they have is the one we just had before, or the left-hand side. This expression on the left-hand side is really just the one we had up here, where we have divided by sine of theta. So when theta is equal to pi over 5, or theta is equal to 3 pi over 5, then if we do calculate sine of 5 theta, then we get either sine of pi, let's say it like this, or we get sine of 3 pi, and doing a quick unit circle in our heads, both sine of pi and sine of 3 pi, they are equal to 0, so we get 0. And that means that thanks to what we have above, then sine of 16 sine of theta to the 5 minus 20 sine of theta cubed plus 5 sine of theta is 0. But sine of theta itself is equal to either, let's say it like this, either it's equal to sine of pi over 5, or it's equal to sine of 3 pi over 5. Both of these are definitely not 0. So when this expression has a common factor of sine of theta that is not 0, we can actually divide with it on both sides. So dividing by sine of theta, we get 16 sine of theta to the 4 minus 20 sine of theta squared plus just 5 is equal to 0 divided by whatever sine of theta is. That's still 0. And then we are ready for the finale. So we have shown that when theta is equal to pi over 5 and theta is equal to 3 pi over 5, then this equation is fulfilled. But this equation, and I shit you not, looks like a quadratic equation where, so let's go CII, if we look at this equation, 16x squared minus 20x plus 5 equals 0, then what we have just shown has roots that are sine of theta squared for theta equal to pi over 5 and theta equal to 3 pi over 5. This is the upshot that we have to kind of see to solve this, is that the equation up here is what happens when we take sine of theta squared and shove in to this equation as x. And then we're in a completely different chapter. Then we think, when you have the roots that are sine of theta squared, and it looks a lot like they want to multiply these roots, then we think, well, we have this rule that the product of the two roots in a polynomial, they are equal to the constant coefficient divided with the coefficient to x squared. So 5 over 16 is equal to the product of the two roots, which is sine of pi over 5 squared times sine of 3 pi over 5 squared. The product of the two roots that this polynomial has is equal to the constant coefficient over the x squared coefficient. And that leaves us with, well, since sine of pi over 5 and sine of 3 pi over 5, both of those angles are smaller than pi, so their sine values are positive, then we can actually take a square root on both sides and say the square root of 5 divided with the square root of 16 must be equal to sine of pi over 5 times sine of 3 pi over 5. And what do you know? That is what they wanted us to prove. And yeah, I hope you enjoyed the ride.